Let's say this is a house where we live. So that's the roof and that's the window. And then that is us inside the house. Now, we need to use electricity for lighting, for computers, for television, and so on. This electricity is usually, depending on which country we are in, it's usually either about 100 volts or 200 over volts. Now, the electricity has to be generated somewhere, and is usually generated in a power station which is quite far away. So there's some power station, probably big factories, people working there, lots of machines and AC generators and so on and so on. Usually very far away, many kilometers, maybe 50 kilometers or more, thereabouts. Let's just say about 100 kilometers away. Now, from this power station, the electricity has to be carried over this tens or 100 kilometer distance over to our house, and must be carried using some wires. Okay, so there are these wires that carry the electricity from the power station to our house, and then it will go to our appliance, our electric appliance like lights, television, and so on. It will go there, and there can be many connections. Okay, and then it must come back, of course. It must form a complete circuit. After flowing through all the appliance, it has to come back and travel over this 100 or tens of kilometers all the way back to the power station. Okay, so there is this power station here which generates the voltage. Okay, alright, so it generates some voltage. Now, the usual way this is done is that the power station will first generate this voltage at a few hundred volts. Okay, so somewhere maybe between 100 to 1000 volts or so will be generated using some AC generator and some energy source like coal or steam and so on, and it then be changed using a transformer to a much higher voltage. Let's see. Much higher, maybe as much as over 100,000 volts. Okay, there must be something that a transformer is used to transform this voltage to 100,000 volts. and then it is carried using the electric cable all the way to a place, a much smaller station, somewhere close to our house, maybe a few kilometers away. And in that station, this 100,000 volts is then changed using a transformer, changed down to 100 or 200 overvolts, so that we can use it in our house. Okay, so the usual way to do it is that there must be a transformer here. There must be a transformer here. Something what is called a step-up transformer. Okay, we've learned that a transformer has primary and secondary coil, and that they're related by the number of turns, the number of primary turns and secondary turns in the windings in the transformer in an earlier video. So it's possible, it can be done. It can be depending on how many turns we use in the coils in a transformer. You can transform it from one voltage to a different voltage. And the transformer near our house, must be a transformer near our house that change this very high voltage to the much lower voltage that we need to use. And so this is called a step down transformer. It just means transformer that converts a higher to a lower voltage. Now that seems like a lot of hassle. Why would we want to step up to such a high voltage, which looks really dangerous? Take it all the way over that 100 kilometers. Surely, if someone touch it along the way, that would be very dangerous. And then why do we have to go through the trouble of changing it back to 100 volts? Now the reason has to do with saving energy. The reason is that if we change this to a very high voltage, then the actual current that would flow through the cable become much smaller. And it has to do with the equation, the power equation that we have learned. P equals to IV. As you can see, for a given power, if the voltage is high, the current must be low, because we multiply the two numbers. Okay, so if I use a transformer to change it to a very high voltage, then the current that actually carries the electric power only needs to be very low. And the reason why we want a very low current over this very long distance is to reduce the heating in the wires. Suppose that the total resistance over this wire, this electric cable over this 100 kilometers is given by R. And then there will be heating in the wire. There will be heating in the wire, and the heat loss, right? The rate of heat loss can also be calculated by the same power equation, the same equation here, except that we would use the current in the wire and multiply it by the resistance in the wire. So I squared R. Okay, we must be careful that the I squared R in this case is not equal to the IV in this case, because the power here would also include the power that is used in the house, but the I squared R here would only calculate the power that is converted to heat along the cable. Since R is we are taking R to be just the resistance of the cables, and it does not R does not include the resistance of the appliance in the house. Okay, so by reducing the current, we can reduce the heat loss. So that's why we want to step it up to a very high voltage. Now in this and maybe the next video or so, I want to work out an example to really convince ourselves that this idea is indeed correct, and that there is indeed a lot of saving in the heat loss. In fact, I will actually show that if we don't do it this way, if we don't step up the voltage, if we simply send 100 volt or 200 volts directly from the station to our house, there is so much heat loss. There's so much heat loss that the heat loss would actually use up more power than the power station would generate. So in order to do this, carry out this calculation, we need some numbers. We need to know the resistance. We need to calculate the current. So we need some values for the various things, like the power from the station, the resistance, and so on. So let's start. Now I'm going to start by assuming that there is actually no transformer. I'm going to assume that there's no transformer, and I'm going to calculate how much heat is lost. Okay, so no transformer. Now, and I'm going to take it that the power station would generate 100 volts and then send 100 volts directly to our house over this 100 kilometer piece of cable. Right, and then I shall calculate how much heat is lost. Right. Okay. Now I will not take it that the power just come to our house. The power would the electric cable, before at some point before it enters our house, the cable must also split into branches. All right, then meaning that there will also be connections from the cable that goes to other houses. Right, so this will go to other houses. So there'll be lots and lots of other houses. Another house there, another house there. So lots of houses needs to be supplied by a single power station, not just our own house. Okay, and so on. So this means that the power station has to generate a lot of power, right? And typically a power station might generate power of the order of well, maybe not typically. It must be very different from place to place and country to country. So I'm just going to assume, make an assumption that this particular power station generates a power, an electric power of, let's see, of 1 million watts. So 10 to the power of 6 watts. Okay, suppose that this is the amount of electric energy that power station supplies. and it will supply many houses around our own house. Okay, so we have power, we have voltage, we have let's see, this distance. Now we need the resistance. Okay, we need the resistance in order to calculate how much power is lost in the cable. Now, to get an idea of what the resistance value is, we can use the resistivity equation. Recall from many videos ago, rho is the resistivity, and we have an equation that relates them. R is equal to the resistivity of the metal times the length divided by the area. Okay. So for the resistivity, I'm going to assume aluminum. Right. In many countries, in order to cover very large distances, these cables are often supported on very tall towers, right? On very tall towers over very large distances, right? Rather than being put underground. I guess if you want to put the cables underground, that would involve a lot of digging, which might be quite difficult as well. So they are often supported by this very tall support, and these cables typically would be very thick. They would have very thick cross sections. Let's say that the cross-sectional area, suppose that the cross-sectional area, call that A, is about 10 cm squared. Let's say it's about 10 cm squared. So that's a very thick wire of maybe an almost solid piece of wire with say about a width of 3 or 4 centimeters, and the length L would be 100 kilometers, and it's often made up of aluminum because aluminum is quite light. It could have been made up of maybe copper, I suppose, which is a better conductor, but the aluminum has the advantage of being a lot lighter, especially if you are going to hang it up on these supports. And as we'll see after I've done the calculation, it's not going to make much difference if we do it this way, because it's going to take up really so much power that it's not going to work. So the aluminum resistivity is 2.65 times 10 to the power of minus 8 ohm meter. Okay, so that's aluminum resistivity. Now with this, we actually have enough information to estimate the resistance. Now it is convenient to first estimate the resistance for 1 kilometer. Right, there is actually a typical value that is useful. So that's what I'm going to do first. I'm first going to estimate the resistance for 1 kilometer, and I'm going to multiply it by 100. Okay. So suppose that L, I'll start with this exercise where L is 1 kilometer, so that's 1000 meters. And using these numbers, I want to find the resistance of 1,000 meters of this aluminum wire that has a cross-sectional area of 10 cm squared. Okay, so substituting these numbers into here, I have for the resistivity 2.65 times 10 to the power minus 8 times length is 1,000 meters, and the cross-sectional area is 10 cm cubed. So 10 cm cubed would be 0.001 meter, 10 cm squared. 10 cm squared would be 0.001 meter squared. Okay, so therefore this is equal to, now if you work out the powers of 10, you'll find 10 to the power of minus 2. So the answer is 2.65 times 10 to the power minus 2. Now, it's easier if I simply take this to be about 0.03. I just take this, round this off to 3, and this gives me 0.03 ohms per kilometer per 1,000 meters. So this is per kilometer. And that makes it really easy to calculate the resistance for 100 kilometers. All I need is to multiply this by 10, by 100. That would give me 3 ohms. That would give me 3 ohms. But that's 3 ohms one way though, and it has to come back again, so that will be another 3 ohms. So altogether 6 ohms. So therefore, the R here is about 6 ohms. About 6 ohms. Now, to make it easier to calculate, I'm just going to take this to be about 10 ohms. Okay. So now I have a value for this resistance, and I'm actually ready to calculate the heat loss. So let's start on that. Clear this off. Now, and I'm going to make the numbers simpler, I'm going to assume that the mains power supply is 100 volts. Okay, so that's used in some countries. 100 volts. So this power station is going to try to send current through this at 100 volts. Right, it's going to send current through this at 100 volts. Now, it will probably need to start at a bit higher than 100 volts because there's this resistance, this voltage drop across this resistance that it needs to overcome. But it's only 10 ohms, and our appliance in the house would often have much higher resistance. Even our light bulb might have a higher resistance. So I'm just going to take it as about 100 volts, and I'm going to calculate how much heat will be lost through heating in this 100 ohms. Now, and it is this 1 million watt that we need to send out, not only to our house, but also to our neighbors and our neighbors' neighbors and so on, everybody living around us. So what I need to do is this. In order to calculate the power loss, I need to find the currents. Okay. Now to find the currents from the power, I can use this equation. P is equal to VI. So the voltage supply here, this is the V, and the current is what I want to find, and the P we know is 1 million watts. Therefore, the current is equal to P over V, and that's equal to 10 to the power of 6 divided by 100, which is 10 to the power of 4 amperes. So we have a huge current going through here. Okay. And now I want to calculate the heat loss in the wire. So the resistance of the wire is R, so the power would be equal to I squared R. Now just a word of caution, we can't use the VI formula for this calculation, because the VI, in this VI formula, the voltage here is the voltage across not only the cable, but also all the other appliances in the house. So the voltage would include that. So if I use VI, it will give me the wrong answer. I will just get back the original 10 to the power of 6 watts. But if I use I squared R, right, the current is correct because it's the current that travels through the cable. But the R, we are using only the R of the cable. We don't include the R's in the other appliances in our house. So this is the correct formula to use for the heating the cable. So let's carry through this calculation. I is 10 to the power of 4, 10 to the power of 4 squared, and R is 10 from there, times 10. And the answer is 4 times 2 is 8, plus 1 is 9. So the answer is 10 to the power of 9 watts. Now you might notice that we have a problem. The power that we are sending out is 10 to the power of 6 watts. And 10 to the power of 9 watts is going to be lost in the cable. In other words, that's 1,000 times more power than what we are sending out. So even before the power, the electricity the power has traveled maybe part of the way, all the power would have been lost. So this is just not going to work at all. If you're going to send out, if you're going to do it this way, it's not going to work at all. Right? So the only way out is to think of some way to reduce this heat loss in the cable. And the only way that we know of, at least an obvious and straightforward way, is to use a transformer to step up the voltage before sending out, so as to reduce the current until it is small enough that the heat loss is acceptable.